Good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. I'm Francesco Petruccione, and I have the pleasure to introduce you to Professor Balázs Szendrői. I hope I got it more or less right. Yeah, Balázs is originally from Hungary, but he studied in the UK. He did his PhD in Cambridge, and over many stations, Warwick, Utrecht, again Oxford, and probably a few hours others in between. He's now based at university in Vienna. Yeah, he's working on algebraic geometry, but this evening he will speak about another passion, which is art and mathematics, and he will try to convince us that mathematics can be fun if you're interested in tiles and similar geometric configuration. Yeah. So Balázs, we are very happy that you made it from the long way from Musenberg to here for this event, and we are very curious to listen to your talk. Thank you very much.
Thank you. Can you hear me well? Yes, fantastic. Thanks very much for coming. It's a real privilege to speak here. I've been coming to South Africa for a number of years, and it's always fantastic to visit, and it's great to come to Stellenbosch in particular. So yes, I wanted to share with you a passion I have, a special interest, but it actually connects to my research, and I hope to convince you that not very far from the ideas that I am discussing, there are really interesting questions that lead directly into contemporary research. But let's start here. So when I thought how to summarize my aim, then the idea that the words that came to mind were this phrase of geometric patterns. So this talk will be about geometric patterns. And here is the first one. Do you know what that object is? Do people know what that object is? You should know it, and you should be proud of it. So this is one of the oldest known examples of a geometric pattern. There is no doubt, really, if you look at this stone, that these are not random marks. And in fact, a rather detailed study was made of this piece of stone because it's super exciting. And to the extent anyone can really ascertain this, it is very clear that these marks were intentionally drawn. It was found in the Blombos Cave, not very far from here, found in Still Bay at the Western Cape, about 70,000 years old. And it really is the oldest. So the birth of abstract thinking is here in South Africa. I learned this trick from Neil Turok, who often starts his talks in this way, but it's a very nice way to start a talk. It all started here. And so this is a geometric pattern, and there'll be perhaps more beautiful ones, but the idea is already here, that we're talking about abstract geometric patterns which are somehow pleasing to the eye. They are used, we don't know, of course, what the person thought when they marked this stone. We have absolutely no idea. But it doesn't seem to have been any practical use, really. Okay, so geometric patterns, that's going to be our starting point, and they could come from lots of different places. They could come from art, and they will come from art in this talk. They could come from the sciences. They could come, and by that I mean nature in particular. They could come from within mathematics, and I'll give some examples of that later. But really, the source of our patterns could be anything, really. And I thought for a while whether I should put pictures on this page, but I'm not putting pictures on this particular page because I really want to kind of put across the abstract idea. And there's so many different patterns. But the particular angle I'm interested in as a mathematician is classification of geometric patterns. So hopefully you'll understand by the end of the talk what a mathematician means by a classification. It's basically a complete enumeration of all possible cases, if possible. And it turns out that somehow, surprisingly, this is very often possible, maybe more often than you might think. And then, why do we classify? Why do we care? I mean, this is really only interesting if this opens up new connections. At least it's interesting for me if it opens up new connections to other areas of math, to science, and so on. And now, on this abstract slide, I wanted to add one more word, which is the word symmetry, which was also in the title. So for this talk, I'm particularly interested in symmetric patterns. And I will explain what that means, but which is a restriction, and nature often provides us with non-symmetric patterns, and they're super interesting. This is not that talk. So this talk will be about patterns which also obey a certain amount of symmetry. So that's kind of the the thesis slide if you want, and our starting point will be patterns in art. So that's where we'll start, and I'll try to lead you through various aspects of this page, really. Okay, so then here is where we start in terms of our art, Islamic art. So I hope that you understand by the end of the talk why in Islamic art has some rather special features which make it particularly interesting to study it from the point of view of a mathematician. This is just to create the historical context. So this is the map of the early Islamic world. This is not a history lecture, but of course, Islam was a religion, an ideology, and eventually it came to represent power as well, and it was super successful. So it started with, of course, Muhammad around 620, and over 150-year period, it already took over, and at that point, it really was an empire, Arabia into Asia, into North Africa, and rolled into Spain. So this all happened in a rather short period of time. And initially, it wasn't maybe a very, very deep cultural influence, but over time, the culture and philosophy and religion of Islam had a very, very strong influence basically all over this map. And it didn't stop there. Then there is the sort of mature Islamic world, so maybe the period 1200 to 1500, where it went much further. It influenced a very large part of the Sahel and across North and Central Africa, and then down the coast also into today's Kenya, Tanzanian coast, and down to Mozambique, north of Madagascar. It didn't quite get as far as here. I apologize for that. I didn't make the map. Thank you for that correction. And all over the Middle East and beyond. Now, at this point, it's not one empire. At this point, it's several smaller kingdoms and empires. And at some point, there was Zanzibar was a center. At some point, Kilwa was a center. Of course, there were all the various principalities and sultanates that occupied Spain and then eventually were pushed out. So this is now a more complicated picture, but that's like, in any case, ignoring the labels, that's the broad area where Islam had an extremely strong influence over hundreds of years. So this is kind of where our pictures will come from, all across that area. And I can't fail to start with the Alhambra. The Alhambra is one highlight, but one of the most exciting and beautiful pieces of Islamic architecture and art that was created. This is a palace, a royal palace, royal residence, fortification, built, well, over centuries, but the large part of the most beautiful bits were built in the 14th century. And it's an absolutely amazing place to visit. It's kind of far from here, but you are ever in Spain, you should definitely try and get to the Alhambra. Book months ahead of time because it books out very quickly. So if you go, you should visit. It's in the south of Spain, not very far from Seville, and it's absolutely beautiful. And here are just a couple more pictures. So this is just a courtyard. It's built in a typical sort of Muslim style, that the internal courtyards are even more beautiful than the building from outside. There is some ingenious use of water here in a rather water poor area. So part of it is just how could they create all these amazing gardens. And then moving on, there are these fantastic, this is one of the most beautiful, the Lion's Court, one of the most beautiful courts. And then moving towards the subject of this talk, so if you look around, you begin to see these tilings. I mean, they are tilings. They are bits of the wall are covered in these rather symmetric geometric arrangements, ornamental arrangements in periodic and various other styles. So this is basically the topic of my talk, are going to be the bits that you find here and here and here, and to some extent in other places as well. And this is just a close-up of one corner of the palace. So you go around and you see a lot of this. So there is clearly something abstract going on here, and so something interesting for a mathematician. But let's just not stick to Spain. There is some amazing art and architecture in Africa. So this is the Great Mosque, which this particular building was built or rebuilt in 1907, but this is built on there was a succession of earlier buildings, all built, well, essentially out of sand. So it needs occasional restoration, but also a very, very interesting structure. Not as rich, of course, as the one in Spain, but still super interesting. And then, of course, you go to Iran, and then there are some absolutely amazing architectural monuments there. And if you feel left out, I mean, any place on that map could have pictures like this. So apologies if I missed anyone. But this one will come back. I'll be talking specifically about this mosque later. So I definitely wanted to mention that. Okay, and then if you move on, then you can sort of zoom in. So we have architecture, but then we have decorative art, and we see similar features. So this is a beautiful door. This is held in the Ashmolean Museum in Oxford, in ebony and ivory. Of course, we don't want to make pieces like that anymore, but this is hundreds of years old. And if you close up, you get these very beautiful patterns. And then we get to inlaid stone. So this is an architectural detail. This is actually in Africa and Egypt. Or you get to carpets. This is not a talk about carpets, but let's not forget that all across the region, one particular expression of patterns and art was carpet weaving. This is not that talk, but I wanted to have one piece of carpet there as well. But more to the talk, you have tiles. So this is a pair of tiles from Ottoman Turkey, 16th century. Again, very beautiful and clearly geometric. There is another one, decoration a bit earlier, again on a ceramic tile. Or you get this one. This we'll play with this a little later, but a very beautiful, once again held in Oxford, a very beautiful, quite symmetric but richly decorated tile. Again, I think of Ottoman Turkish origin. And finally, I think this is the last one that I included. That's another tile. Again, we'll talk about the structure here a little bit later, but again, this is a piece of ceramic. No, there's one more. So this is a picture I took in Tanzania. I like this, of course, not as well preserved. This is a tombstone from Kaole near Bagamoyo, and that was one of the local centers near Kilwa. So you go around the East African coast and you see maybe not as well preserved Islamic remains, but some very beautiful and evocative ones nevertheless. So this particular trip was also a trip to an AIMS center. So I'm here to visit AIMS first and foremost, and this was another AIMS trip. So if you do mathematical journeys in Africa, then you bump into pieces of art like this. Okay, so this was a slideshow. So now I want to kind of summarize a little bit what are the general features of Islamic art. And maybe the most important one, and I didn't select these pictures like that, is no representations of humans. And that, of course, goes back to the Quran. So you are not supposed to represent humans in art. And that really gives this art form a very, very special style. So humans are out. Of course, this is completely the opposite of European art. European art begins with Venus of Willendorf, and then from Venus of Willendorf onwards, we are doing humans, right? And Western art, as I understood, broadly Italian art, French art, that will always represent humans. And this is the complete opposite. It's a taboo. You don't represent humans on your walls. Another feature, which I think has come through nicely, is architecture and art always work together. So they don't have, traditional Islamic art doesn't have this idea of a painting or a sculpture. It's all incorporated into the building. It all works with the building. It all works with the light. It all works with how the sun comes in. And this is all part of the experience. So they have this, I think, more holistic approach to what it means to do art. Is you put it in your building, it serves some kind of purpose. I mean, of course, these are not random buildings. These are monumental, ornamental buildings. But always the art works together with the building. Another thing which you saw a couple of times is you can't do humans, but what is very important is calligraphy. So I won't talk about calligraphy very much because it's sort of a different direction, but it is decorative use. I mean, calligraphy could start with just a quote from the Quran, and often they are readable quotes from the Quran, but they're often not. And there is this interplay between something that looks a bit like writing but actually that'll be an example in a minute. Actually, it's periodicized, so it's not really meaningful writing. It's this interplay between words and decorations and periodicity and I mean, a normal text would just be a text, so it would have a very different structure. So you get this interesting interplay between pieces of writing and art. They do a lot of floral images. That's of course a good place to go. If you can't do humans, you draw flowers. Flowers are very beautiful. It's all in their poetry. It's all on their images. But the thing that's of interest to us is they did a lot of abstract geometric patterns. And the patterns are very often symmetric, periodic, and symmetric in certain ways. And they use a lot of polyhedral patterns. I'll explain a little bit later what this means, but they do a lot of straight lines, start with straight lines and polygons in the plane, and then they start playing with that and base their art on the use of polygon or polygon patterns. Okay, so let me talk a little bit about symmetry. And I think you have different backgrounds. So if you're a mathematician, then this will be a little bit simplistic, but I thought I should I should have some sort of starting point for where symmetry starts. And symmetry is this kind of picture. So we've all drawn this as kids, and maybe at some point we realize that if you flip the paper over, then it's the same picture. So this picture will have this vertical reflection symmetry. If I draw it perfectly, then the left and the right are completely symmetric. And that's sort of roughly what we humans look like as well. We are approximately vertically symmetric, not completely, and if you lose an arm, then even less. But generally speaking, we are left-right symmetric. And then we are not horizontally symmetric. So if you turn something upside down, then you get a very different picture. So this picture will have a vertical symmetry, but not a horizontal symmetry, same as humans. And then you can sort of tell the same story about a tile. So this tile has this axis as a reflection symmetry. If I flip left and right, then it's the same. Now, of course, I mean the idea. I mean the abstract thought. Of course, as a physical object, it's chipped here and it's not chipped there. So that will break the symmetry. But the intention here was that it should be a completely symmetric picture. If you see, all the details are perfectly done. And if you spend some time looking at this, I mean, you can't but be struck by the fact, like, just how good these artists really were and in making these pictures. And another symmetry that this picture has is this rotational symmetry. So if I rotate this 2 steps, so this is a hexagon, if I rotate it 2 steps, then I am symmetric again. I've got the same picture again. I have to do it like 2 steps, 120 degrees, because of these 3 flowers. But if I rotate that image again, I get the same image, and that's rotational symmetry. So these are the basic types of symmetry that you can have. And then here starts our first classification project. You know, what are all the symmetries that are possible? So we have reflection, we have rotation. Maybe the square has a rotation by 90 degrees as a symmetry. We have translation, and that's very important if you talk about periodic patterns, that this is a pattern that I can translate 1 step, and then I am again, I've got the same pattern again. And then maybe this last one is the most interesting and tricky one. There is one called glide reflection. So if I take this thing, I can flip it over in this axis, but then it changes, like it went down, up, and then it's going to go the other way. But then I can shift it half a period along, and then it becomes itself again. So this is called glide reflection. It's not essential for the talk, but it is important to mention it because this is really the last type. Because then we have this thing called the classification of symmetries in 2 dimensions, which is our first theorem. A mathematician would call this a theorem, and it just says that every 2-dimensional Euclidean symmetry, so symmetry of our normal plane, is one of the following. It's a reflection, a rotation, a translation, or a glide. So these are the only possible symmetries that you can have. And then you can say, okay, well, that's good. That's one symmetry, but this is not really very interesting, is it? So let's do symmetric patterns. That's why we came from. And so the first type of symmetric pattern that you might want to look at are what's called friezes. That's perhaps the simplest possible kind of mathematical symmetry. And what's a frieze? So in this picture, there are at least 3, but I could have probably marked that one as well. So friezes are things that happen in a long line, essentially, but they have a bit of thickness to them, but they happen like horizontally. Now, I should make it very clear. The Islamic art did not invent any of this. Friezes in particular go way back to the Greeks, at least. I'm not aware of it before, but certainly Greek architecture, if you look at a Greek temple, they will have friezes running around the front as well. But what was special about Islamic art is the richness of the decoration and the games they played with these patterns. So here is an example. So I'm taking this one out and magnifying it. Okay, it's not a perfect picture. It's my own picture. It's rather hard to take pictures in the Alhambra because everything is kind of high up and everyone is pushing up on you. But this is already one of these I mentioned that I believe this is some sort of writing. I can't read Arabic writing, of course. So I don't know whether this says anything, but it's certainly repeating. So it's certainly a pattern that is made into a repetitive pattern along this line. So this is the same as this and the same as that, and then this repeats here and there, of course, with little mistakes because some of it has come up. I mean, these are 600, 700, 800 years old, so it's amazing that it's still there. But here is this other example. I showed you these tiles before. I mean, this is what you see in the museum, but if you can play graphics games with it, and this is almost certainly by its structure, it's almost certainly a freeze tile. So they would have had it, imagine your bathroom, and then it just runs around the edge, kind of at the top of your tiling. So this is almost certainly the way you should imagine this actually being in use. So this is a freeze tiling. And then you can ask, so this is clearly periodic, so things get repeated. And mathematically, what we would say is that this freeze tiling has translational symmetry. So if I translate one step, then it's the same tiling. Now I should say here, again, we are making some kind of abstraction here. Really, the actual tiling that really has translational symmetry is the infinite tiling. I'm supposed to be able to push it along infinitely long, and no one has an infinitely long bathroom. But the point is that its mathematical structure is still, if you were to continue it, you would certainly get a periodic pattern, or my friend Zura would like to say, I should say partial symmetry at this point. This is another image that you saw before. This is the door. I mean, it's just a door, but again, if we want, we could play with it and we could make it periodic. We could just extend it infinitely out. It would, again, be a very beautiful frieze-like pattern. It has translational symmetry, but it has now other symmetries. So it now has reflection symmetry, actually, both with respect to horizontal and the vertical axis. So it has a richer set of symmetries. Whereas if we go back to this guy before, this does not have reflection symmetry. It's not up-down symmetric because there are these details in the decoration, which if you flip over, it doesn't work. And you might think, well, maybe it works with a glide, it works with a shift, but even that doesn't quite work because this thing is different from that one. So the only symmetry this guy has is the translational symmetry. This guy has more. So this is a more symmetric configuration of translations and reflections. And then here is another one. So here I've just taken the edge, and you can magnify that, and that's also a nice frieze. So it kind of goes around, but once again, we can imagine that it goes kind of horizontally, periodically, and then it fits into our scheme. And here's the next classification result. So this is a classification of frieze symmetries. So this is once again an abstract mathematical result, and it says that there are 7 types of configurations of different symmetries. So starting from this one, where the only symmetry is I can push it along, all the way to here, where I have horizontal and vertical reflections, there are 7 possible configurations, and they're all different. So this one, for example, has a glide symmetry. This one has a translation and a rotational symmetry, and so on. So you can play with this. This is an example that's often actually studied in like elementary courses in group theory. This is really a classification of 3 symmetry groups. So a mathematician would call a symmetry configuration a symmetry group, and this is a complete list of groups of geometric symmetries. But if you don't like technical terms, it's just configurations of possible symmetries. And you can populate this. So you can say, here is this guy that only had the translational symmetry. Here is that guy that had translation and reflection. Here is that guy that had this particular configuration, and I think I did one more. Yes, this is where our floral pattern lives. So you can then take your examples and put them into the scheme. So that's how such a classification result works. Okay, so we can move on and we can think about this guy. So what is this? So this is a tile, and this will tile the plane. Hexagons will tile the plane. If you repeat it over a big surface, now you imagine your bathroom wall, and then you can just put down the tiles. And once you fill it in, you really lose the structure. So I haven't done anything here. I've literally just copied that tile, but it's really rather wonderful, isn't it? Here you really don't see the hexagons. It would be lovely to have a bathroom with this. I can go back and forth. I'm really not cheating. If I take out the lines, then suddenly this much more homogeneous arrangement jumps out at you. So that's kind of one possibility, but it has this triangular symmetry. I can rotate it around 120 degrees, like this individual tile had that symmetry, but the whole configuration has that same symmetry. If I rotate the whole arrangement by 120 degrees, I get the same picture. So it's not only the individual tiles are symmetric, but also the whole arrangement. And then, of course, it has translational symmetry, because that's basically how we built it, right? We took one tile, I literally just copy-pasted that one hexagon, pushed it in different directions. So from here to here, you just literally translate. And the first one is still there, and then you translate it. So this whole arrangement also has a translational symmetry. So here's another one. This is from the Alhambra. This is an actual tiling. But you can play the same game. You can put in the lines, and then you can see the actual tile. So you can see the basic tile, which, I mean, it is even possible that they worked with a quarter of that. But let's say this is our basic tile. And then you push it along and copy-paste. Well, as I say, this was done backwards, but you get that same arrangement. And this now has square symmetry. So this has the rotational symmetry, where I, for example, hold on to my arrangement here and swing it around 90 degrees, then the whole picture moves into itself. And there's lots of other symmetries. It has all the reflectional symmetries. If I pick out that line and reflect, that's another symmetry. Okay, so you have a whole variety of tiling patterns. So these are just pictures from the Alhambra. You walk around and you spot different patterns. And then this is a more scary table. So this actually goes back to a particular mathematician, Yevgeny Fedorov, from 1891, a Russian mathematician. It was rediscovered a couple of times by George Poyer and others in the early 20th century, but he had it all. This is a classification of tiling patterns. So it's a very similar classification result to the 7 friezes. Now the answer is there are 17 different classes. These are sometimes called wallpaper groups, because I like the word tile better, but in the 20th century we moved over to wallpaper, so then people started calling them wallpaper groups. But these are all the different configurations that you can have. So there are some basic ones. There's a hexagonal tiling, and then there is the square tiling, which is represented here by a slightly different picture. But then you can start decorating your hexagon in certain ways. Actually, this is a rich picture, and it's a quite nice topic for an undergraduate thesis, or maybe with a bit of an extension for a graduate project. And it's easy to get lost here, and it's easy to, there's a lot of detail here. There's a lot of nice detail here that you might want to understand. And then once again, it's really a classification of two-dimensional tiling groups. And then once again, we can start populating this. So there is one P1, that's the simplest one, that the only symmetries you have there are translations. So we have translations in 2 different directions. And at least if you take into account the colors, then this arrangement will only have that symmetry. Here we have the square symmetry guy. Here we have it's not quite the hexagonal symmetry one, but it's the one where the hexagon symmetry is a little bit broken. So this guy happens to sit here, that guy sits there, that guy sits there. And amazingly, you can even put, I kind of put 2 copies there. You can even put the Blombos cave picture, which is basically the triangle, the regular triangle lattice that fits into this arrangement as well. So so you can sort of populate this. And I may have got some of this wrong. It's very easy to get this wrong. It's very easy to put things in the wrong place. But I looked at the literatures and I tried to, yeah. So don't copy me on this slide. But I want to make one point though, which is very important, and which is an Islamic, an artisan, a Muslim artisan, someone working with these patterns would not recognize this picture. They never thought in these terms, of course. This is a very, very modern point of view, looking back on what they did. They would not be able to even articulate, I don't think, that there are 17 types of patterns. I'm sure artisans knew the pattern or 2 or 3 that they learned from their masters. But what is amazing, though, is that they got them all. So I didn't populate the whole picture, but actually, even just in the Alhambra, you can find symmetries for all of the 17. So just the artisans, and that must have been hundreds of people who worked there, but just those guys knew all the 17. Well, sorry, I repeat it. Those guys created pieces which correspond to all the 17 different configurations, which is quite amazing, I think. So, I mean, this 17, there's no reason for why there are exactly 17. This is not some kind of magic number in mathematics. This particular problem happens to have only these solutions. But it is very interesting that intuitively and through trial and error and trying one thing and another and building different configurations, they got them all. Right, so I mentioned polygons, and so this could be a talk in itself, and actually that's the side of the subject I knew much less about. But they have also created amazingly beautiful patterns starting from polygons and starting from configurations of polygons. Basically, polygons arise from drawing lines on the plane and then building things up. So I want to show you just a couple of examples. So, for example, this one. But this, I think you saw it in the corner of one of the pictures, actually, but here it is in magnification. So absolutely stunning arrangement of these abstract patterns on in this kind of tiling form. And then this is, I said the Friday Mosque in Isfahan will come back. So this is from Iran. I've not been here, unfortunately. I would love to, but so this is a picture I got from the internet. But there's a lot of intricate polygon geometry going on just in there, and this goes back to the 12th century again. So a long time ago. I mean, this could be straight out of a math book. I mean, illustration for a textbook. I mean, there's an amazing amount of stuff happening there, which they just put there as decoration, illustration. Whatever. So here are some. Again, I copied this from Jay Bonner. Is an amazing architect, mathematician who studied these patterns very much. Actually, if you Google this kind of thing on YouTube, people will show you how to do this. So modern artists create art using these patterns, and there are some really funky ways. You start with a few lines, and then you fill it up, and then eventually you get to very, very intricate, complicating interlacing patterns. But all it started from is some squares. You drew some squares, so sides of squares, you connect them up, and then you start breaking up some of the lines in different ways. And what emerged are these really very, very interesting, complicated patterns. So it's this side of it is an art unto itself. But one thing that really got people very excited is this science paper. So this is a science paper from 2007, where a couple of mathematicians looked at this and looked at some examples very, very carefully, and they made these very interesting, rather radical claims that by 1200 a conceptual breakthrough occurred, and by the 15th century the tessellation approach allowed some of the artisans to construct nearly perfect Penrose patterns 5 centuries before their discovery. So that's a very interesting claim. And you look at the paper, so I should say this is something I've been reading about for a while, but I'm really not a specialist here. But if you look at the paper and read the paper, and they create these beautiful examples, and eventually they start drawing things which really look like they could be out of a book on Penrose tilings. And really, there's one thing I wanted to point out, which is a very important part of this subject, is that if you do traditional symmetry arrangements, maybe I'll flick back. So if you go back to this picture, the thing that's striking about it is that it has hexagons, it has triangles, it has squares. Well, they're not drawn as squares, but this could have been drawn also as a square. It doesn't have pentagons. So there is something called a crystallographic restriction, which says that in these symmetry groups, you never get a pentagon. You cannot have an order 5 symmetry. And if you know anything about Penrose tilings, then you probably know that Penrose's starting point was exactly that. Can you do something with order 5 symmetry? And somehow intuitively, of course, they didn't like that. They wanted polygons of all sides, and in particular, clearly a lot of, what have I done? Yeah, good. A lot of the thinking of these practitioners, of these artisans and artists has gone into thinking about order 5 symmetry. And this is a decagon, this is a pengon. So somehow the starting point here is they were thinking about the same, they had exactly the same starting point as Penrose. They wanted to have pentagons, they wanted to have polygons with 10 sides, because why not? They're pretty, they're nice. 5 is, I'm sure, a special number there also somewhere, and that was their starting point. Now, then you go into the literature, and then you go to this paper of J. Boyner, and J. Boyner doesn't quite believe that. This individual may have been the first to discover the tiling potential of the Penrose rhombi, but there's no evidence that Muslim artists were aware of the non-periodic potential of this design methodology. Fair enough. So they didn't quite get the Penrose tilings, but they got incredibly close. And I think that's already quite amazing. So Penrose tilings is a large, very, very interesting and beautiful chapter of late 20th century mathematics. And there they are 500-600 years earlier, and they almost got there. Okay, so where am I heading in this talk? Where I want to head is go to 3 dimensions. So everything so far, because we were tiling, everything so far was about 2 dimensions. I want to go into 3 dimensions, because that's where we live ultimately, right? We have 3-dimensional teachers, and we might want to say something about the sort of space that we live in. So the basic symmetry of 3-dimensional space, which is already a very, very interesting and non-trivial operation, is rotation around an axis. So, of course, we do that when we spin, if you can spin, or, we do that a lot when we are rolling a ball, or we are rolling a barrel, then that's basically rotation around. You can think of it as rotation around an axis. So that's the fundamental operation. And this really is a very interesting operation, because 3-dimensional rotations are, mathematician would say, fundamentally non-commutative. So it's a structure which fundamentally has some very rich mathematics built into it. So the group of rotations of 3 space is a very, very interesting mathematical structure. But nevertheless, there is still classification results we can do, because mathematics is powerful and is able to identify structures. So one classification result I just want to briefly explain is classification of 3-dimensional rotation groups for the specialist with a fixed point. So this is the starting point, where you want to classify rotation groups which all preserve at least 1 point in the space. And so that's a very famous result that goes back to Felix Klein, the German mathematician, in 1884. So basically, here's the list. So you can have the symmetries of a cone. So like we had on the picture before, this cone I can rotate around. This is a cone based on a regular hexagon. So like with the hexagon, I can spin it around 6 times, and then I get back to itself. Or you can have prism symmetry. So if you have a prism built on a regular polygon, then okay, this is getting a bit more interesting, because I can I have the vertical symmetry axis, but I can also put some horizontal axis. I can, like a barrel, I can kind of turn it over, and that's a different rotational symmetry of this prism. And then there are what's called the symmetries of the regular solids. So that in itself is a very beautiful story of mathematics, and already in here that hides another classification result, which is actually goes back 2,500 years, or give or take. It's written up in the very famous book of Euclid, but possibly it goes even before, and that's called the classification of regular solids into 5 types. So the cube is the 3-dimensional body that we all know, and we roll it around when we play board games. Then there is the cone built on the triangle. The mathematical name for that is the regular tetrahedron. That's maybe some board games also have four-sided dice, so then you will have a tetrahedral dice, or I mean, that's still a fairly common structure that that you will likely to meet somewhere in real life also. And then there are these three more exotic ones, which are not so common: the octahedron, the dodecahedron, and the icosahedron. These are the remaining ones. So none of them look like football, by the way, if you don't get too excited. The football is a semi-regular body. If you actually look at a football in your hands, that's got hexagons and pentagons. I want perfectly regular bodies which have same sides everywhere. So the pentagons are allowed here, but you must only have pentagons. So the regular football is not one of these. It could be. I mean, you could just about build a football out of a dodecahedron or an icosahedron, but it probably wouldn't roll very well. So this has fascinated people for a long time. So these five, and it's amazing. I mean, that's another incredible intellectual achievement. As I said, almost 2,500 years ago, Euclid has an essentially modern proof of this classification. I mean, to turn it into textbook proof, you have to add some details. But he knew this list, so he was not like the artisans. He was a mathematician, and he knew this list, and he would recognize this picture. And this picture is essentially in his book. It's very interesting. It's not in his book. He really describes all of them, but he didn't bother drawing them, which is already quite interesting. There's no three-dimensional pictures in Euclid's book, but in words he describes them all. So he knew this classification, and people, of course, I mean, this picture comes from some medieval book where they try to associate maybe the forces or the underlying principles. So there is fire, and then there is the sun, and there is I don't know, animals and whatever. So people try to, 5 is a small number, so maybe 5 is the solution to nature, and then you try and match 5 things to 5 other things. But mathematically, there's no question. There are five regular solids here, and you get the different groups or different symmetry configurations that correspond to these possibilities. So why is this interesting? So, okay, mathematician would say that here live something called abelian groups, here live something called dihedral groups, and here live something called exceptional groups. This is just for my mathematician friends who probably know this anyway. But I wanted to make, and this is going to be the most technical slide, but I did want to make this slide because this is really what connects to my research. So I'm just repeating the list: the abelian groups, the dihedral groups, and the exceptional groups. And there was an amazing observation of John Mackay in 1980 that there is a precise recipe to relate these symmetry configurations, these symmetry groups, to something called Dynkin diagrams. So Dynkin diagrams is a piece of mathematics we teach to probably in a master's course on Lie theory, and it's a fundamental pattern of mathematics. So these diagrams, these little graphs, come up a lot in different areas of mathematics, and the fact that Mackay connected these pictures to these really quite simple three-dimensional symmetry groups is amazing. And this observation opens up connections to all sorts of mathematical theories and modern physics. So the algebras lead you straight to quantum groups, to algebraic geometry, to operator algebras. So this could be the start of a completely different mathematical talk, but I just wanted to make it clear that if we start from this very simple idea, let's just classify three-dimensional rotation groups, you basically identified one of the fundamental features of mathematics. And this is better than the 17. So I said before that the 17 was a bit of a random number. This kind of 2 infinite series, and there are 3 examples here, that's not random. That really is a fundamental pattern of mathematics. Okay, let's move on. Classification of 3D space groups. So this is now the equivalent slide to the one about the 17 groups. Now there are 230. So these are the possible configurations of 3-dimensional patterns. And so that's got a very interesting story. So about 1892, this was worked out by Fedorov. We had Fedorov before, the same guy who did the plane case, and mathematician called Schoenflies. There was some earlier work of other people, but basically they both wrote out the list and they both got it wrong. Not much wrong, but a little bit wrong. And then they started corresponding, and over about a year, in interesting correspondence, they nailed it all down. They said, okay, actually, you have some repetitions and you're missing some, and they were collaborating. And this is a kind of very nice example of an international collaboration. And they, in a year or so, they tied down the complete list. So this is the complete list. So, okay, I mean, there's a lot of information here. This is what it looks like. So if you zoom in, then this is what you begin to see. Now, okay, you see some patterns. These are three-dimensional patterns. So I can't say that I'm finding this very easy to read. If you actually want to understand it, then if you go on Wikipedia, you can click on any one of these, and then you just get that description, that particular description of what that group looks like. So what sort of symmetries does it have? Order 2, order 3, order 6, order 4. You still have the crystallographic restriction. You're not going to have order 5, but they can be put together in many different ways. But what's interesting about this picture is that there is some other subject creeping in here. So you can start to see chemical equations or chemical formulae here, and names of materials. And of course, that's why this subject is studied, because it's crystallography. So crystals grow in nature, and crystals grow in nature according to very precise rules, and they follow these rules of mathematics. So, and every one crystal can only grow in a certain type of way, or maybe one or two ways, depending on, there are some compounds that are able to grow slightly different forms, but by and large, if you have your chemical compound, that will only be able to build one of these. And so once again, I haven't checked, but my understanding is that essentially all of these can be represented. Now, I can't quite zoom in here, but you can see some very long names here. So it is almost certainly the case that some of these will only exist in the lab, but most of them will exist in nature. And so if you zoom in further, then, this is example 148, dioptase, dioptase, and it's just one example. We have all, I think, held crystals in our hands. You get pyrit, which has got the cube arrangement. This is a more interesting one, which has these prisms, and the symmetry of each of these prisms corresponds to 148. So 148 is this one. So whatever symmetry that has, dolomite would be another example, but dioptase is nicer, so I picked this one. If you go in on Wikipedia and look up dioptase, you'll get the answer that its symmetry group is R3 bar. So it's that example. So there we are. There we have this this whole scheme. So we started with art, but we did a little bit of the sciences. We did a bit of chemistry. We did quite a lot of mathematics. Apologies, that's my subject. But we had a lot of different patterns with symmetry, and we've gone through 4 or 5 different classification results. These are theorems of mathematics, and then we've begun to see some connections to different areas. So if I actually want to populate this picture, so amazingly it all starts 70,000 years ago. Then we had one stop about 2,500 years ago. Then we spent a lot of time thinking about Islamic patterns, and then we got to this 19th century subject, which is crystallography, the symmetries of crystals, and that of course motivated this classification result. But once you kind of jump over to mathematics, you can classify all these geometric patterns into these different theorems, the 7 freezes, the 17 two-dimensional patterns, wallpaper patterns, the classification of three-dimensional symmetries into these 3 types, or the 230 space groups, and then you can build connections to other subjects. So you can build connections to algebra. Well, a lot of this is algebra, but you can build connections to other kinds of algebra, non-commutative algebra, the algebra of Lie groups. Lie groups will take you straight to mathematical physics. Of course, you have materials, you have nanoscience, because if you're building a crystal, you'd better understand its structure. But also I put image recognition here, because image recognition is a subject where you really want to understand 3-dimensional motions. You really want to understand 3-dimensional rotations, because what's image recognition? It's a 2D picture of a 3D image, or many 2D pictures of the same 3D image, which are related to each other by rotations. So understanding this group called SO3, so the group of rotations of 3 spaces is somehow a fundamental question in image recognition. So there are all these connections where we really started thinking from very simple geometric ideas. Thank you.
Yeah, thank you very much for a fascinating talk. I'm sure we have plenty of questions. Anyone who would like to go first? Zura, I knew we could count on you.
Thank you very much for a very beautiful talk. Do we know anything about dimension 4?
Yes, the classification has been done. Yes, so beyond space groups, I mean, as usual in mathematics, the number starts to begin to grow. In fact, I wanted to look this up and I forgot the number. Yes, so 4, 5, 6, these have been classified for some. Yeah, so, you know, mathematicians are mathematicians. They grab an example and they generalize it to one higher dimension. So yes, there are lists in 4 dimensions. There is certainly a reasonably human readable list. After that, it's probably beginning to look very wild, but with computers, you can probably do this. So yes, it has been done. The examples grow very fast.
But there is no, I guess there is no pattern whatsoever.
There is in this space groups, that doesn't seem to be a pattern, no. So the 7, well, the 7, I mean, the 7 is sort of 1.5. I like to think of that as like the 1.5 dimensional example. So 1.5 to 2 to 3, you go from 7. I mean, these seem to be, yeah, I'm not aware of any pattern there. You can do the classification, you get some very large number of examples. I mean, 4 dimensions is still, of course, interesting. I mean, 4 dimensions is space-time. 4 dimensions, people care about 4 dimensions. So yes, I mean, I'm not aware of any direct use that classification has had, but in slightly different directions, yes, things have been classified. But it is rare that you see such beautiful crisp structure. The 2-dimensional, so the 3-dimensional rotation group case is really rather special. That has this beautiful pattern. You lose that pattern in other directions. But yes, classifications can be done. Yeah.
Thank you.
Any other questions?
I don't know if this is a question really, but what about if you work with other kinds of geometries?
Yes, no, that's another talk, but yes, absolutely. So hyperbolic geometry has, of course, many more tessellations than so hyperbolic geometry is huge, and you can tessellate it in much more interesting ways. As you know probably better than I do, that's the theory of Fuchsian groups, and so yes, hyperbolic geometry already in the plane has a lot more space, and 3-dimensional hyperbolic geometry, that's all, sorry, this is now a off-topic specialist discussion, but then you get into first-term geometries, and then, you know, very quickly you get to very advanced mathematics. So yes, absolutely. On the sphere, there's again a smaller number of possibilities. Sphere is basically the same as 3 space with a point, so that's going to be the same. But once you go into hyperbolic space, then the possibilities are endless. And that has been used in art, not of course by Islamic artists, but M.C. Escher, the Dutch artist, inspired by Penrose, has done some very beautiful art based on hyperbolic tilings, hyperbolic tessellations. So yes, there are many more options because hyperbolic space is so much bigger and has so much richer structure.
Yeah, if you don't mind going back to the slide about the freeze tilings, because I didn't understand like the precise technical distinction between the freeze tiling or the freeze group and the wallpaper group, like why there's 7 and the 17. What is the technical distinction?
So the technical assumption for a freeze group is that it has one translation and compatible reflections and rotations. And so, I mean, this is what I mean by 1.5 dimensional, that you're kind of assuming that it's a subgroup which has generator, one translation generator, and then maybe some, and then the 2-dimensional one has to fix a lattice. So it has to fix a 2-dimensional lattice. And that's where the crystallographic restriction comes from, that if you fix a lattice, then you can only be order 2, 3, or 4, or 6. So it has to fix a lattice in the plane.
Here we go.
Hi. So the slide about the glide symmetry at the very beginning, that the pattern was also translation symmetric. Is there an example of one that's translation? That's glide symmetric, but not translation.
No, because 2 glides combine to a translation. So if you have glide symmetry, you do it twice over, it's a translation. So no. So as soon as you have something with glide symmetry, you're built in some slightly bigger translational symmetry. Yeah. So this is, but that's a very good question. I mean, the point is, you may imagine that, let me have an order 3 and an order 4. Then you're ready, then you can't do it. So, there are ways to put these together. And if you put them together in certain ways, then you get one of these patterns. If you want to say, can I have a glide without a translation? The answer is no, because, there's a lot of rules. There's a lot of internal structure here. So this is why there are relatively few possibilities. You might imagine I could combine it this, and this, and this. And the answer is either that there is no such animal or that it's one of the ones that you already know. But in hyperbolic space, there are many more ways to put things together. So there are more examples. But there is, symmetries is a surprisingly constrained area of mathematics. That it's group theory has a very simple set of axioms. It starts with just like a few lines. And it's a very rich subject because there is so much internal structure there, so many constraints. So if you say symmetry, you might think I can do lots of things, but there are not so many things you can do actually. You start building things and they either break or they become something that you actually had before.
Do we have any question from the online audience? While that is.
My question is of a different kind.
Okay.
Why, in your opinion, human beings love symmetries so much?
I'm sure books have been written about this. I'm not the expert. I don't know what is aesthetically pleasing. I have a friend who we could invite here who thinks about the perception and psychology of perception, and I'm afraid I'm out of my depth here. I do like them because I'm a mathematician. I think, but look, I mean, why do we like periodicity? Again, that's a very, psychological, philosophical question, but that is very clear that, there's a lot of periodic phenomena that humans observe, like the sun goes up and goes down, the moon comes up and goes down, periodicity is so much built into human existence that time periodicity is something that I think you kind of observe, and animals observe that. I mean, we know that animals are very sensitive to time periodicity. Spatial periodicity and patterns is a little bit different, and I'm not sure there is an immediate link, but again, see a row of trees. I mean, that's, so these visual patterns you get from nature, even before you get to crystals, which is quite an abstract one. Beyond that, your guess is as good as mine. As I say, I'm sure there are people who could answer more deeply. I can't answer you more deeply than that, but it is built into human existence somehow, and the way we observe things around us and the way that we identify patterns is part of what leads to abstract thought, and that somehow requires at least some periodicity. But as soon as you have periodicity, you're beginning to get patterns. But maybe one more thing to say is if you go back to the origins of writing, I mean, the origins of writing, at least according to some theories, so writing, for example, emerged in Mesopotamia, and it started actually with tallying. So writing and counting kind of came together. The first clay tablets are basically tallies of animals. They say, I have 5 sheep, but as long as you do 5 strikes, that's a pattern as well, right? So you maybe wanted to record your number of cows, but you never draw a full cow. You say 1, 2, 3, 4, 5. And that's an abstract move, and that's a pattern. So, but leave it at that. But it's very clear that these things somehow arose together at the dawn of human history.
Must not forget that apparently there are people that love chaos. So
absolutely, absolutely. Non-periodicity and non-symmetry are also extremely important. And thank you. And of course, what humans actually would see as beautiful has to be a bit of both, right? If you saw a person really completely symmetric, I think that would freak us out because that's not like we want some symmetry, but we want also some irregularity. So some things that we actually find beautiful are always going to be a mixture. And thank you for that reminder. Absolutely. So and that's really how art often works. So this is particularly striking that this is not how the Muslim artisans, they didn't do that. Very often they really followed the pattern, and they followed the pattern over meters and huge facades of mosques, and they followed the pattern. So they had this very particular interest in symmetric configurations.
Donovan, do we have questions from the online audience? Please go ahead.
We've got 2. The first one says, Crystal phase transitions often occur where the space group of a material changes with temperature by a reduction or increase in symmetry. Could the possible changes in symmetry be described mathematically so that we could work out what kinds of phase transitions could occur?
It sounds like a fascinating question. The short answer is I have absolutely no idea. But again, I think at least some, I'm not aware of exactly this kind of work. And I have to say, I never really studied crystallography. I'm an amateur on the crystal side. But one thing I know that has happened, which is a little bit different but related, is you can also create new shapes from old shapes by grinding. So when pieces of material grind against each other. And that I know that there have been studies of how the shapes changed. And it's not exactly about symmetry and not temperature, but more physical impact, more grinding. But I know that studies have been done there, and that's super interesting, connecting the mathematics to the dynamics of the physical phenomena. The particular question that asks sounds super interesting. I don't know. I can try and look it up, whether there is some literature on that. I was aware vaguely of this fact that the same material can take different shapes, but if it's under temperature, that sounds amazing and super interesting. And I don't know.
Yeah, the second one says, are there any non-periodic symmetries in Islamic tilings?
Well, the literature was on the board. So I think experts don't completely agree on that. I think the authors of the science paper would say more or less yes. The author of J. Bonner, who studied this a lot, would say not really. They were there at the cusp. And of course, it's very hard to be certain, because if you look at the paper, there's even some pictures that they analyze of buildings that in the 19th century were still there, but they're no longer there. I mean, these are objects that are hundreds of years old, sometimes 1,000 years old. They're pretty vulnerable. So it's hard to be certain. And it's hard to be certain because you have the examples. I think the strict answer is no. I mean, there are no aperiodic tilings in the Penrose sense. That's very clear. They didn't have that. But they had something which almost got there. And this paper convinced me that they were really one step away from it. But I think what's key is that they've done the fundamental mental step, which is to think about order 5 symmetry. So that's something there's a lot of pentagons among these polygonal tilings, not tilings, but among these polygonal patterns. So they certainly made that intellectual step of why can't I do a pentagon? I want to do a pentagon. And that is the first step. If you look at Penrose's book, that's how he started. He wanted order 5 symmetry, and so did and the Islamic artisans wanted pentagons. So they certainly took one intellectual step, but no, I don't think they created a fully quasi-crystal tiling in the Penrose sense. No, they didn't do that. But it sounds like they got very, very close. And these are the two papers that one could read for and against and make up your own mind.
If there are no more questions, then thank you very much. And as a little sign of our appreciation, I want to give you a copy of a magazine that NITheCS co-publishes. So
thank you very much.
Thank you very much
for
your talk. Thank you.
Thank you
very much. Thank you.